Hey everyone, so in this clip we're going to be talking about how to derive something very important that you will be using all the time when you get into pre-calculus, trig, AP calculus, any courses like there or beyond. We're going to be talking about the power rule. So the power rule is so named because it seeks to get the derivative of k times x to the n plus c, c being some constant that we don't know. It's convention in calculus to put that, like for example, if you're doing integration, you're going to see that a lot. But okay, so we're trying to find out what this derivative is, and notice here, by the way, as well, that y equals k n to the x, or kx to the n. So this is called the power rule because it's trying to find the derivative of the form of a power function here, and this is named like this to differentiate it from the exponential one, because this time we're going to have some kind of a constant in the exponent, not the variable itself. And once we do the derivation, we're going to figure out that this is going to equal n times k times x to the n minus 1. So basically, the idea of this is you're taking the exponent and putting it as a constant out here, and you're going to decrease the exponent by 1, and the derivative of a constant, as you'll eventually find out in your coursework, is 0. And also another thing you're going to learn at some point is that if you take the derivative of something that you could split into like an f of x piece and a g of x piece, for example, then you can evaluate it in pieces and come to this conclusion anyway. So because that's something that we can do. So let's say our f of x is y equals k x to the n plus c. And so what are we going to do with this? Well, the concept is that if we're going to find the derivative of this, we're going to figure out what happens when we take y and x and apply an infinitesimal change to it. So we're going to look at what happens at y plus delta y, delta being from Greek, and it's commonly used in mathematics to indicate change. So you're going to be seeing this notation a lot. So we're just going to add the delta pieces in here. So now we're going to have a k times x plus delta x to the n plus c, because we're taking both y and x and they're going to change an infinitesimal amount. And eventually we are going to have to take the limit as delta x approaches 0 of change in y over change in x in order to find out what our dy dx piece is. This is another way to just say your ddx, or your derivative of whatever you're looking at with respect to x. So how are we going to go about this? Well, notice here that this piece should look familiar to you because this is in the form of something we can take the binomial expansion of. So binomial expansion, if you saw my other clip, then you would know that taking the binomial expansion of some a plus b to the power of n is going to yield us a quantity of a to the n plus some n times a to the n minus 1 times b plus n times n minus 1 divided by 2 factorial times a to the n minus 2b squared plus some n times n minus 1 times n minus 2 over 3 factorial. Again, these n pieces here are going to be your coefficients, which are going to go in line with those values for whatever row you're looking at on the Pascal triangle. So multiply this by a to the n minus 3 times b cubed, and that's going to go all the way down to b to the n. If you want to learn more about this, check out the other video that I made. So this is what we're going to expand this out with here. So we have y plus change in y equals k times what we're going to make this whole piece out to be. So we're going to have a is our x here, so we're going to have x to the n plus n times x to the n minus 1, and then our b, if you can see up here, is our delta x. Okay, and continuing this, we're going to have n times n minus 1, and you're going to see what's about to happen here, that we don't actually have to multiply the n pieces out because they're eventually going to just go away anyway. It's all going to collapse to 0. So this is over 2 factorial times x to the n minus 2 times delta x squared plus n times n minus 1 times n minus 2 over 3 factorial times x to the n minus 3 times delta x cubed all the way down to delta x to the power of n, and this whole thing plus c, because we have to include the constant there at the end. So okay, now what we can do is we can just multiply the k out to all these terms. So let's go ahead and do that. Y plus delta y equals k x to the n, and because of what we're about to do next, I will put the c with this piece because you're about to see why that's important after I write this out. So plus kn times x to the n minus 1 delta x plus kn times n minus 1 over 2 factorial times x n minus 2 times delta x squared plus kn times n minus 1 times n minus 2 over 3 factorial times x to the n minus 3 times delta x cubed plus all the way down to our k times delta x to the n piece. Okay, so what else can we do here? We'll actually notice here that k x to the n plus c, that's just what we got for y. That's what our y is that we're using. So if we subtract y from both sides, then it turns out that y goes away and this goes away for the kx to the n plus c, because that is equal to y. So after we do this, then we're going to go ahead and get this in the form of delta y divided by delta x, which means that we have to go ahead and basically take every single term and we're going to divide by one single delta x. So this is what we're going to do with this. So delta y over delta x equals kn to the x minus 1, and we're dividing by delta x here. So delta x divided by delta x is 1. So we're going to have 1 times that, and that goes away. Okay, so now that should be an n minus 1. And for the next one, we're going to do kn minus n minus 1 over 2 factorial times x to the n minus 2. And notice the delta x squared divided by delta x is just going to give us delta x. And now onto the cubed part, we're going to add plus kn times n minus 1 times n minus 2 over 3 factorial times x to the n minus 3. And delta x cubed divided by delta x is going to be delta x squared. And that goes all the way down to, notice we're taking 1 away from the last term here. So k times delta x to the n divided by delta x is going to be represented as k times delta x to the power of n minus 1. So now we have to take this part up here in order to find what our dy dx is. So now we're going to say dy dx equals the limit as delta x approaches 0 of this entire piece. So just copy this part down. So k n x to the n minus 1 plus k n to n minus 1 over 2 factorial times x n minus 2 delta x plus k n times n minus 1 times n minus 2 divided by 3 factorial times x to the n minus 3 times delta x squared plus delta dot k, k times delta x to the n minus 1. And now we're going to go ahead and evaluate this. So we are going to see what happens when delta x approaches 0. So dy dx is going to equal kn the x minus 1 plus kn the n times n minus 1 over 2 factorial times x the n minus 2 times delta x. But notice how delta x approaches 0 now, so that part is going to go to 0, but notice how it's multiplied by this whole piece, so this is going to contribute 0, so that goes away. And now we have to do it to the next term. So kn, we're going to add plus kn times n minus 1 times n minus 2 divided by 3 factorial times x to the n minus 3 times delta x squared, but notice how delta x goes to 0, therefore delta x squared has to go to 0 and it's multiplied by that piece, so that goes away, plus delta dot k times delta x to the n minus 1, and notice how it's still going to 0 for the delta x, so 0 to the n minus 1, that whole piece goes to 0. So what are we actually going to be left with? Well, dy dx equals k times, well actually, usually it's represented as putting the n first, so dy dx equals n times k times x to the n minus 1 when y equals k x to the n plus c. Okay, so that is how we come to the conclusion that this is how we evaluate the power rule, or this is how we get the power rule equation that is very well known, and you're going to be using it pretty often because this is very important for like anything that involves polynomial or something like this. Then the power rule, even if it's got a polynomial piece in it, since you can do derivatives in pieces, then you're going to be using this a lot. So hopefully you found this helpful, and come back for the next one where Joe shows you how.